All right, so vectors. You can give me a definition of what a vector is from physics. Anybody?
It has direction and magnitude.
Direction and magnitude. Okay, so a vector is going to look like, for you, a ray. Remember a ray from geometry or algebra 1 or whatever? It wasn't a line with an arrow going both ways. It was like a point and then an arrow going one way. But an array, what we really mean is, I'm going to point it, but it really goes forever, right? So a vector is a little bit different in that the actual length that we draw the vector means something. Okay? So when he says direction and magnitude, what he means is the actual direction that the vector is pointed, that means something, okay? But also the length of the vector means something about how big or small a force it has, or a speed it has, or whatever the magnitude is measured as. Okay? So I could measure it as like if a wind is blowing in a certain direction at a certain strength. If it was a really mild breeze blowing towards the north, then maybe I represent the vector with a tiny vector pointed north. If it's a really strong breeze blowing towards the west, or blowing like the Gulf, the jet stream, which is a huge current of air that moves across our country and the world, for that matter, across the globe. Like if you get up in a plane, for instance, in the jet stream, like I don't know if you've ever flown to Denver, but you can fly to Denver nonstop in about 3 hours and 45 minutes, but you can fly back in about 3 hours and 15. So the actual stream is it's slowing you down 15 minutes one direction, it's speeding you up 15 in the other, but that's a big current, and it can move like 100 miles an hour. It's like the East Australian current in Finding Nemo, you know, where the turtle gets in the current, right? And once he's in the current, he's just moving with the current. Well, you have vectors like that, or forces like that move, but you're going to show that vector's strength or quantity of the force. And again, whether that's in miles per hour, or in newtons, is how you measure force, or in work, or whatever it is you're measuring, the length of that vector means something. Are you with me on that? Now that doesn't mean I'm going to be asking you, I'm going to look at your paper and go, no, your vector's too short. It's not like that. We're rarely going to be drawing a lot of vectors. Most of the stuff we're going to be doing is the math of it. Okay, the analytical side of the math. And I don't think you're going to have a problem with it if you learn and keep up daily. And hopefully that's going to be a difference when you're here every day, as opposed to, oh, I'm at home, Tuesday, it's so pretty out, or whatever. So now that we're stuck here, and we're getting this stuff daily, hopefully we'll keep up better and that kind of thing. Also, you can start turning in your homework daily also. I don't want to do everything on test day anymore. And if you should get quarantined, we'll turn it in when you get back, or email it to me if you want to send pictures, but hopefully that will be the case. So I'm going to go through a bunch of different things on this vector sheet, but one of them is not the formula sheet. The formula sheet's kind of a quick look at things. It doesn't have everything on it that we're going to need to know, so if you ever see something that's not on your sheet, you might want to add it to it. I have added over the years, but sometimes I still forget things. But we're going to use this as a reference point. Like, we're going to talk about a lot of these first couple things today, and as we move through the next 3 or 4 days, we should hit on almost everything that's on this sheet. But I thought I would put this out there, so if you ever need a reference to look back on it on not on test day, but when you're studying for your test, you'll have that right here. Okay, so this covers all kinds of different things. So should you run into a problem like, hey, how do you find the so-and-so trace? Boom, finding the trace of a sphere. So if you see a homework problem and you're thinking, he didn't talk about that, don't forget to look back at this sheet, because a lot of times it'll have a little reference to something that's small maybe and not super significant, but something I'll need for you to know. So I put that on there. It used to be a one-page sheet. Now it's like 2 or 3 pages. Yeah, 3 pages. So there's a lot of different things we'll learn in this time, but we're really going to pick up today on page 11. All right? So first thing is a vector is a quantity which shows blank and blank. He said magnitude and direction. Okay, some people say quantity and direction, but I like to say the vector is a quantity, so we use magnitude and direction. And again, that magnitude, that strength of the vector can be measured in all kinds of different ways. And you'll see some of those as we move through here. Okay? And I said magnitude could be a measure of a vector's, and I'm just throwing out examples. It could be force, it could be its velocity, it could be acceleration, any unit which we measure the power of something or the size of something or whatever. That could really be the magnitude. And then the last thing I have right here on the little fill in the blank, it says if two different vectors have the same magnitude and direction, they are considered to be equivalent. Now that's a big deal that you lock in on that, because that's a major difference between a ray and a vector. A ray, where you begin is significant. In a vector, when I give you a vector, it doesn't matter where you begin. So if I say, hey, you have this vector, and we'll talk about this in a second, it's you have these little brackets you use, that almost look like inequality signs, but they're these funny little vector brackets. And you might see it looks like a point, like 2, 3, right here. Well, that doesn't mean to start at the origin and go over to up 3 and draw your vector. It means start anywhere and go over to up 3 and draw your vector. So vectors, notice that the condition of a vector is not location, magnitude, and direction. It's just magnitude and direction. So whether I draw a vector like this here, or whether I draw one like this over here, or over here, okay? If I measure the length of it, all right, that would be the magnitude. If the length is always the same, well, they have the same magnitude. And then I measure angle just like I would in trig. I always measure angle from 0 degrees. So if that's 0, if all of these, when you reference them from 0, if they all have the same angle, then they have the same magnitude, the same direction. These would be equivalent vectors. It doesn't matter where they begin. Now, if I'm graphing one, why not begin at the origin? Because it's easier to count for me. But you technically can start anywhere. So wherever you start drawing them, and ask me questions if that bothers you as we move through this. But I normally, if I'm given a number line, or if I'm given an XY coordinate plane, I'll start at the origin, but technically I could start anywhere as long as I had the same angle, as long as I had a certain angle and a certain length. Are y'all seeing that? Okay, so 5 different ways we can write or describe a vector, and I'll talk about the main ones that we see in here. Okay, first one, obviously we could draw a picture of it like I was just doing. We're not going to do a whole ton of that in this class. A little bit, but not a ton. So that would be kind of the geometric side of a vector. And in thinking about it and comparing some things, which we'll do later, I'll show you that aspect. But what we're going to do is the mathy, analytical side. So what we're going to do, instead of thinking of it as a magnitude and a direction, right, length and an angle, work like this. This is how I would write magnitude. It almost looks like a double absolute value. So evidently the length of the vector, say it's 10, and the angle of the v, angle of the vector 60, that would basically be saying, okay, this has a length of 10 and the angle is 60. Okay, I could draw a picture of it, or I could talk about it like this. And we're going to do a little bit of this, okay? Now, so a lot of times I won't give you a picture, I'll just tell you about it in that manner. But what we're really going to do a lot of is convert this magnitude and a direction to actually what we call a component form. It almost looks like a point, except it doesn't have parentheses, it has a funny little inequality looking bracket. And all that says is move 5 to the right, like you would a point, and then go up 5√3, like you would a point. And then from the beginning of wherever you began to the end of wherever you ended, you draw a line with a little arrow at the end. Y'all with me? So the only difference is instead of going over and up and putting a point there, you go over and up and you draw a vector to there. Y'all seeing that? And again, it doesn't mean that you have to start at the origin, because a vector doesn't show magnitude, direction, and location. Just magnitude and direction. You can start anywhere you want as long as you move those 2 amounts. Y'all seeing that so far? Okay, and we call that component form. There's another form that we like to use called unit vector form. Now, don't let unit vector form bother you. Unit vector form uses what we call the unit vectors. And I and j, and also k when we get to 3 dimensions, which is not difficult, it's just 1 extra dimension, you'll see. All right, so I and j for now represent movements in the x direction. So this tells you to move 5 units in the x direction. So if I was sitting there by itself, the letter I means move one unit to the right. And since this by itself has no j, that would mean move nothing up and down. So this right here, if you just saw a single I, that means move one unit this way. Well, this has a 5i, so what does that mean? Move 5 units that way. That's all that means. But if I were to just write it like this, you see, duh, I'm moving 5 units that way. Now the j means move 1 unit up. So nothing left and right, but 1 unit up. So if I were to ever see 1j by itself, that means don't move left or right at all, just move 1 unit up. Okay? And if I have a k vector, that means I would have to extend it to 3 dimensions. And that's like if you had an x-axis, a y-axis, and then a z-axis coming out. So if you did have that, you would have to be including all 3 dimensions. But that would mean nothing on the x, nothing on the y, and 1 on the k. And if I went to 3 dimensions here, I'd have to also probably go to 3 dimensions there as well. But bottom line, that's what I, j, and k mean when you see them. We'll talk a lot more about that later. But if you really look at these 2 things, is there really a whole lot of difference? This is saying move 5 to the right and move 5√3 up. This is saying move 5 unit vectors to the right, same thing, because you're 1 unit. This is saying move 5√3 unit vectors up. Same thing. But don't confuse these 2. Don't put i's and j's in those brackets. Don't put brackets around an I and a j. Don't put pluses in here. This needs to look like a point, and this needs to have no parentheses and no commas and just a plus in the middle. Are y'all seeing these? These are literally just forms. It's like standard form or slope-intercept form. They mean the same thing, but they're just different ways of writing the same thing. Are y'all with me so far? Okay, now, last method, which we're going to get to later, but I'm just throwing it out there now, is called trig form in some books. Some books call it polar form. If you're like, what the heck's polar form? In some books, we cover polar coordinates or polar graphs right now, and then we cover this stuff later. But I'm covering this right now because I think it makes polar a little bit easier at times. But if you look at this right here, it looks like this is what we call polar form. This would be what we call the magnitude of the vector, right? That's the magnitude. That's how fast I'm going or how strong the force is. And then I have cosine theta I plus sine theta j. Cosine theta and sine theta, that would be the angle of the vector that goes in right here. Well, if you look at this, this is called trig form. But look what happens when you multiply it in. If you do multiply a 10 times a cosine 60, guess what cosine 60 is? Half. So what's 10 times a half? 5, so you get 5i. And what's sine of 60? Square root of 3 over 2. What happens if you multiply a 10 times the square root of 3 over 2? 5√3j. Isn't that unit vector form right here? So bottom line is, the normal progression of actually finding these forms is you start off with a magnitude and a direction, and you put it in trig form. That's trig form with the 10 on the outside, not what I have in red. 10 on the outside, cosine theta I, sine theta j added together with parentheses. But if I were to multiply the 10 in and simplify, now I have unit vector form. And then if I have unit vector form and I throw the I away, and I throw the j away, and I throw the plus away, and I put a comma in between them with the funny brackets, then I have component form. But they all are different ways of saying the same thing. Are y'all with me on that? When we get into complex numbers, complex and polar form, you'll see this a lot more, except you won't see I and j, you'll just see the I over here. But this I does not mean imaginary. Make sure you get it in your head that I just means when we're in this chapter, it's a movement left or right, a j is a movement up or down.
What is the number out front? Is that always 10 or is it always a 9?
It's always whatever the magnitude is. And these angles will always match because those are always the direction angle. So yeah, if the magnitude was 20, put a 20 out front. If the angle is 40, put a 40 there and there. And if you can't simplify it, if you don't know what sine of 40 is, which I don't either, then just leave it as sine of 40. Okay? Are y'all with me so far? I'm just kind of doing some housekeeping right now on vectors, throwing some definitions at you, and then we'll get into actual computing a couple things. Okay, so the first thing I want to talk about is magnitude. And magnitude, we use the little double absolute value things, and there's kind of a reason for that. When you see complex numbers, you'll see, oh, that's kind of like, well, you might remember this. Do you remember how to find the absolute value of a complex number? Anybody? Do what? Yes, because you may not remember this, but imaginary numbers by themselves have a real component, which means you went over 2, and you have an imaginary component, which means you go up 3. So it's kind of like plotting a point, okay? And if I wanted to know the absolute value means the distance from origin on a number line, or the distance from 0, except I have a plane. But if that's over 2, and that's up 3, I would use the Pythagorean theorem to find that distance, wouldn't I? Yes? No? Well, that's absolute value. Well, absolute value being that distance, that's what magnitude is. On a vector, I'm still going over a certain amount and up and down a certain amount. To find the length of that vector, I'm going to do the same thing, except I show it by putting a double bar instead of a single bar. But it is kind of like absolute value. So right here, I'm going to scroll down a little bit. If I started you out with the vector -3, 5, what you need to know is, well, that would mean that I'm going 3 to the left, up 5, right? And then from wherever I begin to whatever I end, draw your vector. But if I want to know the magnitude of that vector, how long it is, or how powerful it is, or whatever it is, I'm just going to be doing the Pythagorean theorem to find its length. That's all magnitude is. So when you see magnitude of a vector like this, you are sent the magnitude. You're going to use the little double absolute value things to illustrate that, oh, I'm finding magnitude. But it's kind of like you're finding just basically the Pythagorean theorem. Okay? So when I give you this, you're going to go, well, if I had drawn a picture of that, that would have been left 3, up 5, from the beginning to the end. I would have drawn my picture. Well, I would have used Pythagorean theorem to figure that out, and I would have gotten, what, a root 34? So for magnitude, I'm going to square the -3. I'm going to square the 5. I'm going to add them together and take the square root. And then if you don't have a calculator, you're fine to leave it like this. Or even if you do, it's better than rounding it. Now, if you see it written like this, is that going to freak you out if I put it in unit vector form? Hopefully not, because writing it like this is the same thing as writing it with the brackets, with the 4, comma, -5, isn't it? Y'all seeing that? Make sure if you use the brackets, you don't have the plus in there. You have a comma, the i's and the j's go away. But either way, this is telling me to do what? If I were graphing it, it would say go 4 to the right, down 5, and draw a vector towards that point. And again, you could start anywhere you want, finish wherever it left you, but I like starting at the origin if it doesn't matter, because it's easier for me to kind of visualize it. And how would I find the magnitude or that length? Tell me. Square the 4. Square the whole -5, right? Don't make it -25. You're squaring a -5 makes it positive 25. Square that whole thing. And again, I don't know what root 41 is, about 6-ish, right? 6.5 maybe. Because root 36 is 6 and root 49 is 7, so something like that. All right, now, also, sometimes you're going to be asked to find a vector between 2 points. Don't confuse that with a vector. It doesn't have the funny brackets on it, does it? So if you see parentheses, that means what it's always meant. There's a point. So if I'm going from 3, -2, which is down here, and I'm going towards 6, 7, which is up here, over 6, up 7, and I can start, it tells me to start here and finish there. How would I write out what this vector is? What did I end up moving? Over what? Over 9 and up what? Another 9? No. Yes. Now, that's pretty easy if I can draw a little picture and sketch it. But what if my points are negative 27, negative 530, positive 62, negative 897? You're not going to be able to draw a good picture of it and count it. So what's a good way to get this 9 without having to draw a picture? What do I really do to find how much I move to the right? Now, distance formula will give me that length, won't it? Which might be great if I want magnitude, right? Because magnitude would be the length of that. But how do I figure out this 9 from these two values right here? These 2 points. Now, if I add them, I get, what, 3, 5? Be specific.
The difference between the two.
The difference. Now, which difference means subtract. Which one do I subtract from which one? Actually, to find the actual length, absolute value would work great. But I got to make sure I'm going in the right direction, all right? Like, if this vector was right up, so I need them both to be positive. But if it was going left down, I would need them both to be negative. So yeah, if all I wanted was distance, that would be great. But I need direction as well to show where I'm going.
The second minus the first.
I'm going to want to go y2 minus y1. Okay, because look, y2 is what here? Like, y2 was 7. So I'm going to take where I'm terminating, where I'm ending, and I'm going to subtract where I'm beginning. So y2 minus the y1 would give me a positive 9. If I do y1 minus the y2, then I get a negative 9. That sounds like I just went down, but I need to be going up. Are y'all with me? So when you're finding these points, you need to be thinking terminal minus initial. Where I'm terminating minus where I'm beginning. So I can observe that it's 9, 9, right? But I really need to be thinking terminal minus initial. So when you see me right here at the bottom, I'm going to scroll up a little bit here. At the very bottom it says, for point PQ, for vector PQ, and notice what did I use above the vector? It looks like a little ray up here, except it really doesn't do it well, this program I have. It's actually not an arrow like this above PQ, it's this. It's like a half arrow to show it's a vector. So this would be the vector from P to Q, which means Q is the terminal, and look what I've done here, terminal minus the initial. So if I'm going from P to Q, and you know I'm going towards Q because the arrow is pointing that way, right, from P to Q. Then Q is my terminal, I got to make that first. P is my initial, I got to make that second. Don't forget your brackets, don't forget your comma. So in this case, because I terminated at 6, 7, I'm going to go 7, Y, and 6. Those are my terminal points. And then my initials, -3, -2. So 7 minus the -2, 6 minus the -3. And when I clean it up, I get the 9, 9. And this is more along the lines of what you'd probably be doing if I had to give you 2 points. And if I don't tell you which one's terminal, which one's initial, you don't know which way the vector's going. Right? I could be going one way, I could be going the other way. So I would have to tell you that. And if I don't tell you, I'm going to write it like this. So what does this tell you? I'm heading towards the Q. That's the terminal. So if I'm ending at Q, I got to begin with Q, with the subtraction. Y'all seeing that? Okay, moving on. Okay, so what if I don't give you the components? I don't give you in unit vector form, and I also don't give you the beginning and the ending point, right? Which doesn't really matter most of the time anyway, because as we said before, most vectors, if I just tell you what they're doing, their magnitude and direction, you could draw them anywhere. So what if I just told you magnitude and direction? Like this. I go, all right, let's just say it's something like wind. The wind is blowing at 20 miles an hour, and its direction angle is 38 degrees north of east or something, or whatever. So 38 degree angle, 20 degree magnitude. how can I find the actual components of the vector? And the components would be these values that go there and there in my component form, or the same values that go in my my something I plus something j form. How do I find those components? Now this part, guys, should be really easy for you because it's just the basic of trig. If I think about an angle, and I know this is 38 degrees, and I know that the magnitude or the length of the vector is a 20, the components just end up being what? My x movement and my y movement. And hopefully we can find that kind of trig, can't we?
Yep.
So if you think about it, I'm going to write this out once, but I hope you don't do it again. I hope you just kind of have this memorized. What trig function could I use that could help me find, say, x?
20 cosine 38.
Say it again.
20 cosine 38.
No. Give me the trig function before you jump to the final part. What trig function would you use? The cosine of 38 is what? Adjacent over hypotenuse? Now, I wouldn't want to use tangent, because if I use tangent, then I have y and x, I have two variables. So I want to use a trig function that uses 20, right? And uses this angle. And if I have an adjacent and I have a hypotenuse, or a magnitude, wouldn't I want to do cosine of 38 as x over 20? So you can see if I did cosine of 38 is x over 20, and I solve for x, can you not see that x is 20 cosine 38? That is the, right there, magnitude is the 20, cosine of the angle, and you can see it right there. Whether it is in this form with the brackets, or whether it is in this form with the I. Does that make sense? Now hopefully you have this part from the unit circle down. What did you do to find the x coordinates on anything on the unit circle? What did you look at? The cosine, right? And what did you do to find the y's?
Sine.
Now why didn't you use the hypotenuse on anything on the unit circle? Why did you just do like cosine 30 and say square root of 3 over 2? Because the hypotenuse is always 1. Well, now that's the length of the vector, right? If you're using your circle. Well, my length is not always 1. If it is 1, then I'm going to have a 1 out there, and yes, x is the cosine of the angle. But if it's a vector with a magnitude that's not 1, just multiply it by whatever the magnitude is. So it's just what we've been doing from the unit circle. X is the cosine of the angle. Y is the sine of the angle. The only difference is my magnitude or length of the movement isn't 1. Sometimes it's 20, sometimes it's 10. So with the same kind of thinking, could we find the y value? Check it out. How would you have found the y value yesterday? You would have said sine of the 38 is opposite over hypotenuse, and you would have multiplied by a 20 and got your y value. Well, I just hope from here moving out you go, yeah, well, I've been doing that. Every unit circle. If I want to know the y movement, I do sine of the angle, right? Well, the only difference now is I'm doing sine of the angle for the y, but I'm also multiplying by the magnitude. Because it's not always 1. In fact, on my work, it rarely will be 1. So, if I'm given stuff, magnitude, direction, you can put it in component form, or you're in vector form by just going magnitude cosine of the angle, magnitude sine of the angle, magnitude cosine of the angle, magnitude sine of the angle. And then just make it fit whatever form you want. Either with brackets and a comma, or with no brackets, no comma, I plus j at the end. You track it with me? Yes, no? Okay. Moving on, scalar multiplication. Now, scalar multiplication, do you remember a scalar from vectors? What was a scalar? I said from vectors. From matrices. Do you remember a scalar from matrices?
It's only going to have magnitude and direction.
Yes. You just read it. I didn't say that.
Physics.
Looks like something I'd say. Oh, okay. So a scalar number, guys, is like when you had matrices, you had all these rectangular array of numbers, and every now and then out front you have a 2. So a 2 just showed a quantity. Maybe you had 2 times this matrix, so you doubled it. Maybe you had 2 times this determinant, so you calculated the determinant and you doubled it. Well, on a vector, it's the same thing. A multiplying by a scalar typically doesn't change the direction. It just changes the length of it. So if you had a magnitude that was like going towards 30 degrees with a length of 10, and I double it, now it's still going towards 30 degrees, but it has a length of 20. That's all it does. Now I can't just say, well, it never changes direction. Because what if I was to multiply by a negative 2? What do you think that does? If I had a vector and I multiply by 2, it doubles the length. But what if I multiply by a negative 2? It doubles the length, and guess what? Reverses it. So I guess it reflects it over whatever normal curve it's coming out of, which we'll talk about normal later. But the bottom line is it just basically completely changes the direction. So instead of going at like 30, it might be going at 180 degrees the opposite direction at 210. Are y'all kind of seeing that? But normally I would say that a magnitude doesn't change the direction, except maybe possibly reversing it if it's negative. So that's what scalar multiplication is. So right here, if you think about this, if you think about the vector 2, negative 5, this would be me sketching 2, negative 5. Over 2, 1, 2, 3, 4, 5. It would look like this right here. Over 2, down 5, right? What do you think happens if I multiply this vector by a 6? I'm going to have to go 2, negative 5, 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 2, negative 5. Well, guess what the net result of that is? Instead of going over 2 once, I'm going over 2 once, twice, 3 times, 4 times, 5 times, 6 times, or 12. Instead of going down 5 once, I'm going down 5 once, twice, 3 times, 4 times, 5 times, 6 times. But it's not really rocket science. I'm just distributing the 6 in. So now I have a big giant vector that is not 2, negative 5, it's over 12, down 30. And if I go negative 3v, same kind of thing. The only difference is instead of multiplying it by 3, I'm going times 3 and then doing what? Reversing it. So it ends up being way over here. But you don't have to think about that. So it ends up being not that at all, but that, or negative 6, 15. And you can see the math. Look, doesn't it kind of look like I went 6 to the left and up 15? Y'all track with me? And same thing with a half. If I do a half of a 2, negative 5, 1, negative 5 halves. So normally, and so instead of that, I'm going to go 1, negative 2.5. I'm going to be right here. So those are scalar numbers, and it just basically is like the distributive property. And adding vectors, and this is the real glory of matrices. It's going to make a lot of the ugly trig geometry stuff that you've done in the past so much easier. What do you think you would do for a 2, negative 7 added to a negative 10, 12? Just take a random guess. Add the x's, add the y's, and there's your vector. And if I had a scalar in there as well, what do you think you're going to do to a 2 times this vector minus a 3 times that vector? Take a wild guess. Multiply it in first. So 4, negative 14. And if I multiply the negative 3, I'm just going to replace it with a plus sign. And then 30, negative 36. And then what? Subtract or add. If you only bring a 3 in, then you can leave the negative. If you bring the negative 3 in, change it to a positive. So in this case, 34 comma negative 50, if I've done my math right. Yes, no? And if you looked at this pictorially, what it looks like I've done is this. And I'm not going to get to all of this today. It's pretty obvious at this point. So we'll pick up with this tomorrow. But anyway, if I'm adding 2 vectors manually, which requires a lot of care and precision, if I give you 2 vectors and say add them, here's what you do. You can pick whichever one you want to be first, lock that in place. And then you take the other one and you slide it over so it connects to that end. Are you following me? So it doesn't matter where they are. Don't move the angles. Don't change the angles. Keep the magnitudes. and you want to treat them like you're on a journey. I'm going from here to here first, and then I'm going to take this and I'm going to go from here to here. I'm going to start at the end of the first and then finish. Well, the result of your vector, which they actually call the resultant vector, would be the distance and the direction you have from the beginning of the first to the end of the second. So this would be the resultant vector. Okay? And there are two ways to do that. What I just illustrated was the head to tail method. Here's the parallelogram method. Take the first vector and then take the second and connect it to the first at the same spot. Draw a parallelogram, which is, I think this is stupid, and then draw a diagonal from these two across to that. But to me, that's the same thing as just putting this one at the tail of the first one and going head to tail, head to tail. Okay, guys, I'm going to pick up. If you get asked anything, guys, listen up. If you get asked anything tonight about finding the unit vector, that's different from unit vector form. Unit vector form is the thing that has the i's and the j's in it. The unit vector, if you get asked about that, or if you get asked about finding direction angles, okay, you can probably figure it out if you read the notes and look at the keys, but you can wait on that. We'll talk about that tomorrow. Y'all have a good day.